Look at this standard linear equation system with three variables. Writing out the x, y, z variables, the plus signs, and the equal signs over and over takes time and clutters the page. To solve complex systems efficiently, we extract only the numbers. We map these numbers into a matrix vector equation. This separates our system into three distinct parts: the coefficient matrix on the left containing our multipliers, the variable vector in the middle, and the solution vector on the right. To move even faster, we combine the first and third parts into an augmented coefficient matrix. We drop the variable vector completely and bring the right side constants directly into the main grid, separated only by a vertical line. Matrices organize your data so you can calculate the solution directly. They take the raw information of the system and format it for a computer or a mathematician to process. Every operation on this augmented matrix follows the exact same mathematical rules as the original equations. Our target is row echelon form, which requires creating a staircase of zeros below the main diagonal. We must clear these three specific positions. We start with the first column. Using the top left number as our pivot, we eliminate the value directly below it. By subtracting 2 times row 1 from row 2, that first position becomes a 0, and the rest of the row updates accordingly. Now it is your turn. We need to zero out the second column of the third row. Pause the video and determine the exact arithmetic step required. To clear that position, we subtract row 2 from row 3. This completes our required operations, securing a clean staircase of zeros below the diagonal. The Gaussian algorithm systematically clears out the lower triangle of the matrix, isolating one variable completely so we can begin solving the system. With the matrix in row echelon form, we look at the bottom row. Translated back into algebra, this row now represents a simple single variable equation. A quick division gives us the exact value of our third variable. We take that known value and substitute it into the row directly above it to find the second variable. Then we carry both known values up to the top row to solve for the first. This gives us our final solution vector. To guarantee our math is correct, we run a check. We multiply our original coefficient matrix by our newly found solution vector. The resulting numbers match our original right side vector exactly. Passing this check confirms that despite the repeated row operations, our final values are perfectly consistent with the original system. If we change the right side constants of a system, calculating everything from scratch takes time. Instead, we can apply the rank criterion to diagnose immediately whether a solution even exists. Look at these two new augmented matrices, both already reduced to row echelon form. We define the rank of a matrix as the total number of non-zero rows it contains. Look at the bottom row of this first matrix. The coefficient side is all zeros, meaning its rank is 2, but the augmented side contains a 5, giving the full matrix a rank of 3. Because these ranks do not match, this system yields a mathematical contradiction. There is no solution. Now observe the second matrix. The entire bottom row is 0. Both the coefficient matrix and the augmented matrix have a rank of 2. The ranks match. But since the rank is less than our 3 variables, we have a system with an infinite number of solutions. Gaussian elimination reveals the matrix rank. This single number tells you exactly how many solutions are possible before you calculate a single variable. We started by stripping the variables from an algebraic system to build an augmented matrix, then applied the Gaussian algorithm to clear the lower triangle. By checking the bottom row of that reduced matrix, the rank criterion immediately categorizes the system: a unique solution, no solution at all, or an infinite set of solutions. You now have the complete set of tools to organize, solve, and verify any linear equation system you encounter.